This recording will go over homeostasis, which is the process that stops bleeding when a blood vessel is compromised. Homeostasis, or the stoppage of bleeding, takes place in 3 steps. First, upon the damage to the blood vessels, vascular spasms causes blood vessels to shrink. For a small blood vessel, these may be enough to begin reducing the bleeding. Step 2 is the platelet plug formation, which plugs the blood vessel, giving time for step 3, which is the formation of a fibrin clot or coagulation, which is a more permanent long-term clot that will seal the damage and give time for tissue repair. So remember that step 1 was vascular spasms. The damage in the blood vessels will result in smooth muscles in the blood vessels contracting due to chemicals secreted by the damaged endothelial cells of the blood vessels. The chemicals are things such as thromboxanes and endothelins. Remember that blood vessels are lined on the inside by one layer of simple squamous epithelial tissue, which is what we call the endothelium or the endothelial cells of the blood vessel. Following vascular spasms comes the second step, which is platelet plug formation. During this step, a positive feedback loop starts, which will result in platelet adhesion, platelets adhering to each other, creating a platelet plug. The first step is that the damage caused by the mechanical break of the blood vessel exposes collagen fibers located in the connective tissue of the blood vessel. A protein circulating in the blood called the von Willebrand factor, or VWF, attaches to the exposed collagen fibers, and in turn, platelets circulating in the blood attach to the von Willebrand factor. So we have this bridge between platelets, von Willebrand factor, and collagen fibers. So remember, the exposed collagen fibers is what initiates the process of platelet plug formation. Following the binding of platelets to the von Willebrand factors, these platelets will become activated and begin to secrete all sorts of chemicals that create the positive feedback loop we talked about. The attached platelets will secrete substances such as thromboxanes, which makes platelets sticky, and they make them also attractive to each other. ADP and thromboxanes are secreted in greater and greater amounts. The presence of the chemicals stimulate the secretion of more chemicals. That's why we call this a positive feedback loop. This causes more circulating platelets to be stuck to the already present ones, and slowly the collection of platelets stuck to each other on the area of injury grow, creating platelet aggregation and eventually a platelet plug. So this picture shows you what is happening. You can see here the collagen fibers that have been exposed due to the cut in the blood vessel. Notice also these are the endothelial cells, simple squamous epithelial cells, that are going to secrete the original substances that are going to cause the vascular contraction. Down here you can see the smooth muscle that will contract in response to the substances secreted by the endothelial cells. So right here, these little contraption here that almost looks like a spring represents the von Willebrand factor. And the platelets, which are these star-looking, oh, sorry, that's not the von Willebrand factor. Let me take that back. Let's see, these little dark rods here are the von Willebrand factors. There we go. And so they are the ones that will bind to the collagen fibers, and in turn, the platelets will bind to the von Willebrand factor. So these spring-looking things are going to be fibrinogen and fibrinogen receptors that allowed the platelets to begin attaching to each other. Platelets that have attached to the area of injury will begin to secrete thromboxanes and ADPs that will attract more platelets to the area and make them more and more sticky. Okay, so we can see here more of the events, the platelet aggregation. Now, thromboxane, the synthesis of thromboxane is prevented by aspirin. So aspirin inhibits prostaglandins activity, which in turn prevents the synthesis of thromboxane. So prostaglandins is needed for the secretion of thromboxane. Again, thromboxane was the chemical secreted by platelets that made platelets sticky and attractive to each other, therefore led to the platelet plug. Aspirin is going to inhibit the platelet plug formation, and that will cause a condition called petechia, or tiny hemorrhages, due to thrombocytopenia. In other words, to the low number of platelets. So that's how aspirin is involved in stopping the platelet plug step in the coagulation or hemostasis cascade. The reason why petechia forms is because at any given time, there are always tiny hemorrhages taking place in the tiniest of blood vessels in our body. But we don't find out about it, we don't know it, because they're immediately being repaired. When platelets are not working properly, these tiny hemorrhages turn into small areas of bleeding, which is what we call the petechia. That's when these little red dots appear on the skin, and they're due to a lack of platelet activity. So that's one of the conditions, that's one of the things that have to be looked at or monitored when someone is taking aspirin for long periods of time. Okay, so we had the hemostasis events as having three different steps. First was contraction of blood vessels of the muscles of the blood vessel, vascular spasms. Number two was platelet plug formation. The third step is the one that's going to create a more stable clot. And this is what we called the coagulation step. What initiates this very complex step is the production of thromboplastin, which is secreted by the damaged blood vessel cells. There are actually two coagulation cascades, what we call the extrinsic pathway, which is the first one that is activated. It will be activated by the thromboplastin released by the damaged blood vessels. Thromboplastin binds to calcium, which binds to a protein called factor 7, and this is going to activate factor 7. Activated factor 7 in turn activates factor 10. Factor 10 in turn activates what we call the common pathway. Now, these are very complex events. You do not need to know in detail what is happening at each step. What you do need to know is that there are two pathways, the extrinsic pathway and the intrinsic pathway, which we will see shortly. You also need to know that the proteins involved in each of these pathways are called clotting factors, and they have numbers attached to them, like factor 7 or factor 10. The numbers are not given in the order in which these proteins in the order in which they act. They're instead given in the number in which they were discovered. That's why you can you will not see an order in the numbering of these proteins. Okay. Now the other point to remember is that all of these factors are going to be made by the liver. Okay. So notice that the last step in this pathway is going to be the activation of what's called factor 10, which in turn activates what's called the common pathway. And the common pathway, we're going to see it here in just a second in more detail, will be the one that will result in the formation of the clot. Remember, we mentioned there were two pathways, the intrinsic and the extrinsic pathway. We saw the extrinsic pathway, and if you noted, there were very few steps. There were about 3 steps on the extrinsic pathway. The intrinsic pathway is longer, and it takes more time to complete. However, it will produce more clotting factors at the end. So essentially what will be happening is upon injury of the blood vessel, the extrinsic pathway will be activated first. The extrinsic pathway is very short and it quickly creates coagulation factors. At the same time, shortly after the extrinsic pathway is activated, the intrinsic pathway is activated, which takes longer, but is going to produce more of the coagulation fibrin proteins. So the intrinsic pathway, it starts with the activated factor 7, which was part of the extrinsic pathway. And I will show you this in a picture here in just a second. I know this is kind of a little bit confusing. Factor 7 activates factor 12, which in turn activates factor 9, which in turn will, with the help of chemicals secreted by platelets, and factor 8 will activate factor 10. Okay. Again, you don't have to know all of these steps. What you do need to know is that both extrinsic and intrinsic pathway end with the activation of factor 10, which in turn activates the common pathway, which is the last steps. Also remember I said that these factors, clotting factors, are proteins, and the order is not sequential. The order is the order in which they were discovered. So notice that factor 12 comes before factor 11, which comes before factor 8, and factor 7 comes at the beginning right here. So again, don't let that confuse you. It's just the numbering of when they were discovered. Okay, this picture summarizes both clotting pathways. Again, let me reiterate, you do not have to memorize them. However, let's look at the important parts. Here's the tissue damage taking place. Okay. Upon tissue damage, the extrinsic pathway, which is very short, is activated first. It only takes a few steps to start with this activated factor 10 that is going to, in turn, set into motion what's called the common pathway. The intrinsic pathway is activated a little bit later, and it does need the extrinsic pathway to continue its activation. It takes more steps, it takes a little bit longer, it ends at the same place. It ends at an activated factor 10, right here, sorry. This is the activated factor 10, which will initiate the common pathway. So this right here is the common pathway, which will be initiated by the activated factor 10. Both extrinsic and intrinsic end in the same place, the activation of factor 10. So let's see what the common pathway is. Once factor 10 is activated, factor 10 is going to activate a protein called prothrombinase, which in turn turns into thrombin. Prothrombinase turns into prothrombin, which activates thrombin, and thrombin turns fibrinogen into fibrin. So prothrombinase turns prothrombin into thrombin. Thrombin turns fibrinogen into fibrin. Fibrins are actually fibers, protein fibers, that are going to be physically involved in the clotting process. So these are the fibers that are actually going to produce the clot. So let me go back one more time. Both extrinsic and intrinsic pathway end in the production of the activated factor 10. Activated factor 10 turns prothrombinase, activates prothrombinase. Prothrombinase turns prothrombin into thrombin. Thrombin turns fibrinogen into fibrin. So once you have the fibrin, these are the fibers needed for the clot. So finally, you will have the fibrin clot. What do you need to know from here? What you need to know from here is that the beginning of the common pathway, the end of the extrinsic and intrinsic pathways is going to be the activation of factor 10. Activation of factor 10 is going to create prothrombinase, which will turn prothrombin into thrombin. Thrombin turns fibrinogen into fibrin. Fibrin meaning the fiber clots that will create the clot. So you need to know, first of all, the steps of the common pathway and the proteins involved. Activated factor 10, prothrombin turns into thrombin, fibrinogen turns into fibrin. Okay. Something else to remember is that the extrinsic pathway is shorter than the intrinsic pathway. Extrinsic pathway starts first. Okay, let me go ahead and go to the next PowerPoint. Okay, so remember that the extrinsic pathway and the intrinsic pathway, both of them end with the common pathway, with the activated factor 10, which creates prothrombinase. Prothrombinase converts prothrombin into thrombin. Thrombin converts fibrinogen into the fibrin fibers. Also notice that calcium and clotting factors, which are made in the liver, are needed for clotting. So when you look back at the picture that we just saw of the cascade, I'm going to point out the calcium all over the place. All right, so this is an actual picture of a clot. The yellow fibers you see are the fibrin fibers created at the end of the common pathway. And what these fibers are going to do is they're going to trap platelets and blood cells, red blood cells especially, are going to be trapped, and they're going to create the actual clot. Okay, let me go back to the pictures of the cascades. I just wanted to point out what was needed for clotting. What we need for clotting is the clotting factors, which are made in the liver. We also need calcium. Notice that almost every step has calcium involved in it. Okay, so calcium is definitely needed for clotting. Okay, so I just wanted to make sure you understood what was needed for clotting. Something else needed for clotting is vitamin K, which is needed for the synthesis of the clotting factor proteins. So this vitamin will go to the liver. This is a fat-soluble vitamin, meaning that it doesn't leave the body easily. By the same token, it's going to be harvested, or we will get it from foods or actually most of it, we get it from the bacteria in our large intestines. So this is one of the vitamins made by the microbiota, the bacteria living in our large intestines. One of the reasons why we want to keep these bacteria abundant, healthy, and happy. We can get a little bit from diet, green leafy vegetables, but most of it we're going to get it from the bacteria in our gut. Remember that the extrinsic pathway is quicker, but the intrinsic pathway produces more thrombin, which will lead to more fibers, more fibrin fibers. Notably, also, the extrinsic pathway can be activated by glass. And you're going to say, who cares? Why do we care about the extrinsic pathway being activated by glass? Well, when you collect blood in a glass test tube, it will clot. And the reason why it will clot is because the glass will begin the activation of the extrinsic pathway. So this will be one way to measure how quickly the extrinsic pathway is going to start working, is by measuring how long it takes for the clotting to begin to be completed. That this also means that when we collect blood in a glass test tube, if we don't want it to clot, we're going to have to add an anticoagulant to the test tube. Okay, so do know the particulars of the extrinsic and the intrinsic pathway. Now, if the body does not need the blood to clot, we will need anticoagulants in the blood at all times to prevent clotting. Clotting may be occurring due to things like plaque or minor internal tears in the blood vessels. So we don't want uncontrolled clotting taking place in our blood vessels. So the blood has natural anticoagulants like heparin and antithrombin and prostacyclins circulating. We do use some of these therapeutically, but as therapeutic anticoagulants are typically synthetic, some of them are actually harvested from bacteria. So heparin, EDTA, and sodium citrate are therapeutic anticoagulants. Now, the clots are there to seal the damaged blood vessel and give it time to repair. Once the repair is finished, the clot must be dissolved. The process of dissolving the fibrin clot is called fibrinolysis, so literally the dissolution of the fibrin. The process is carried out by when plasmin, which is a protein, hydrolyzes the fibrin clot. What creates plasmin is the precursor called plasminogen. Notice that anytime you see these gen at the end of the name of a protein enzyme, these are all proteins, these are all enzymes, this tells you this is generating. So this is the protein that generates plasmin. This is the precursor of plasmin. So anytime you see the gen, you'll know this is the generator of the working protein, which is plasmin. Typically what happens is that the protein may be folded in a way that is not a working fold, if you will, or may have a little portion of it that needs to be cleaved. So these may be plasminogen, and the minute that the area that has to be cleaned is cleaved out, then all of a sudden the protein now folds in a way that actually will work, okay, let's say like that, and now it becomes the working version of the protein. So plasminogen is the precursor, is the same protein that has to be refolded, maybe cleaved, modified a little bit so that it turns into the working protein. So what it's circulating is the non-working version, so that when we need it, the body can just turn it into the working version quickly. Plasminogen is activated by factor 12 and urokinase, lysosomal enzymes. Plasminogen is made by the liver. Most of these proteins are made by the liver. So notice that the tremendous work that so far, just 3 chapters into this semester, we've talked about the tremendous work that the liver is doing. So far, we have seen that the liver is involved in making some of the immune system proteins, like the alpha and beta globulins. We have seen that complement proteins, which are immune system proteins made by the liver. The liver is involved in clotting, creating some of these proteins, all of the factors and prothrombinase, etc., that are needed for the clotting. The liver is also involved in fibrinolysis, so it's not only involved in creating the proteins that clot, but also the proteins that are going to dissolve the clot. The liver also made albumin, which was the protein that kept water inside blood vessels. So notice all of the functions of the liver. When the liver stops functioning, we're going to have problems with clotting, edema, the yellowing of the skin because bilirubin is not being detoxified anymore. Anyway, so just as an aside, I wanted to mention that at this point. Therapeutic clot dissolution, again, some of them are harvested from bacteria like streptokinases. Okay. So this is a quick review of how plasminogen, clot dissolution happens. Inactive plasminogen in the blood is converted to plasmin, and plasmin in turn begins to work on the fibrin clot and dissolves it. So you should know at this point what is hemostasis and what are the 3 steps of hemostasis. Vascular contractions, platelet plug formation, and axial coagulation. Remember the role of von Willebrand factor in platelet plug formation, which was that it bound to collagen fibers, which in turn then von Willebrand factor then bound to circulating platelets and activated the platelets. Remember how aspirin prevents blood clotting by preventing the production of thromboxane, which means platelets are not going to bind to each other and make the platelet clog. Which pathway leads to a fibrin clot faster? The extrinsic pathway. And which one is activated by GLAS? Again, the extrinsic pathway. Both of them activate intrinsic and extrinsic pathways, activate the common pathway. And so be familiar with the components of the common pathway. Let me go back, I didn't mean to do that. And the role of thrombin in the formation of the fibrin clot and in fibrinolysis. Okay, so that concludes this portion of the PowerPoints.